Hello and welcome back. In today's video we'll take a short look at the history and development of databases. It all started in the 1950s with the development of magnetic tape and punch cards, and then the early versions of databases were developed in the 1960s. And then from the 1970s onwards, databases started to emerge that we are still using today. The most commercial ones that are still used were developed in the 1980s, and then further development happened in the 1990s with object-oriented databases and web-based databases. And in the 2000s we had NoSQL databases, and now we're in the era of new SQL databases. Now let's take a closer look at all of those. Punch card and magnetic tapes. So these are the early beginnings of storing data. It started in the 1950s when we had computers and we wanted to persist information. So punch cards were regular cardboard where you really punched a hole in predefined positions, and those positions represented data. Magnetic tape started then to emerge in the 1960s. They started as reels of magnetic tape and allowed sequential data access. In the beginning the capacity was rather humble by today's standards, but 3 megabytes was quite a big deal in the 1960s. In the 1970s this progressed by more than a factor 10. And magnetic tape is still used today, and one cartridge, as it's now used, holds up to 18 terabytes of uncompressed data. Then, in the 90s, IBM developed the hierarchical database model. It was implemented in the IMS database that consisted of the database itself and the transaction manager. It was accessed via a data language or interface, DLI/I, and the key point was that data records are organized in trees. So each record is a node, and each node has multiple children but only one parent. And if you want to find a particular data record, you need to navigate from the root to the desired child. Obviously that has quite some disadvantages. There's only one tree in these very early systems, and you don't have links across trees. And you also don't have links across different layers, which makes it very difficult to model complex relationships. The network model was then proposed in the end of the 1960s by the Committee of Data System Languages, mainly driven by Charles Bachman. Here data are organized as graph structures, so you have multiple parents and children, and data are still stored in the nodes, and the edges, the connections between those nodes, model the relationships. This allows many-to-many relationships as well, and this is more flexible than a hierarchical model, but it did not become dominant later on, because IBM still focused on the hierarchical model, and it was then superseded later by the relational model. This relational model was then developed shortly afterwards in the 1970s, and the seminal paper was a relational model of data for large chart data banks by E.F. Codd. Here data are organized as tuples grouped by relations. So what does this mean? Simply spoken, we can represent the data as tables, and here the columns are attributes, variables or names, like we would put it in an Excel table for example, and the rows, these are the tuples, or as we can also say, the rows hold the values. And then we have different links between tables and attribute that links different of these entities together. So we see an example here on the right for 3 variables and 2 rows. The advantage of this approach is that it has a very strong mathematical foundation in set theory, and this allows strong guarantee for consistent states of databases. The way to interact with this model, or rather with the implementation in a database, is called SQL, Structured Query Language, and this became the standard language to interact with relational databases. So which ones are then used from the 1980s onwards? There are a number of commercial and open source databases that follow the relational model, and they're still very prevalent today. So we have, for example, the Oracle database, IBM DB2, Microsoft SQL Server, and then open source ones are, for example, PostgreSQL, MySQL, MariaDB, SQLite, and many more. In the mid-80s, new research started to focus on object-oriented databases that emerged in the 1990s. Here the information is represented as objects, as, for example, used in object-oriented programming languages. So this is allowed to add persistency to objects and integrate it with the programming language. So you create, store, manipulate objects and have the same representation of entities in the programming language and in the database use. However, this has mainly found use in many niche and specialized applications, has not found use in the wider world. Then, in the 2000s and so on, NoSQL databases started to emerge. The relational SQL databases were very successful, and they're still very prevalent today because of their strengths in, for example, consistency and the strong mathematical guarantees. But these become limitations as well. We will discuss acid versus base later on, but one of these reasons that become limitations is then scalability. Relational databases often struggle with many servers or large and big data set because of the guarantees that it needs to make for a consistent state. Also, you always need to have a predefined schema and data model, and high availability and fault tolerance are hard to achieve with these kind of databases depending on your application. And this led to the emergence of NoSQL databases in the 2000s. And here the development was not so much on the strong guarantees and on the consistency, but on flexible data models, high availability and performance at scale. There are many types of NoSQL databases. NoSQL databases is, if you want, like an umbrella term. So depending on what use case you have, you will choose a particular type of NoSQL databases. For example, you could have a key value store like the Redis database. This is good for small and continuous read-write operations and infrequent updates and simple queries. Or you could have a document store like MongoDB and others. Here you store all the information in XML, JSON or YAML documents. Essentially, this is a subclass of a key value store, and it's almost the opposite of a relational database. All information is in a single document, not in multiple tables that are related to each other. You also don't have a fixed schema, so essentially you treat documents like objects and put this into a database and retrieve these objects one at a time. You also have column-friendly databases like Cassandra and others, and here the data are organized in key spaces, tables, rows, columns. That sounds very familiar to relational databases. However, the main focus is on scalability and high availability and performance. So this means that you have to make some compromises. For example, this is not ideal for complex queries or complex joins between these key spaces and tables, and you also don't have these strong guarantees of relational databases, so you don't have ACID transactions. If you really want to have efficient queries, you need to model your data very carefully, and because it's not a relational database, you have your own query language that is often related to SQL, but only part of it because of the limitations that are put on by the approach of these column-friendly databases. Another approach are graph databases, like for example Neo4j. Here the data are organized as graphs and nodes and vertices. New SQL databases then started to emerge later on, and they are designed to overcome the challenges of both relational databases and NoSQL databases. Right? Remember, relational databases have strong consistencies, but they struggle with high performance or big data. And NoSQL databases, they focus on high performance, scaling and big data, but they're not ACID compliant, so they don't have these strong consistency guarantees. And new SQL databases then address this problem by sort of making relational databases or the approach and guarantees of this scalable across the whole large clusters, and also lead to high availability and leading to handling big data. So approaches here are, for a commercial side, Google Spanner, Amazon Aurora, CockroachDB and VaultDB, and many more open source implementations. So this sounds a bit too good to be true, and in a sense it is. Right? It delivers the performance that is required, that led to the development of NoSQL databases with the strong guarantees of relational databases. The downside is they have complex deployment issues, right? If you want to benefit from the high performance and scalability while returning these strong guarantees and the ACID compliance, you carefully need to design your cluster and your operating conditions and your day-to-day operations of a large and distributed cluster to achieve all of this. So in the end, let us summarize. Databases have a long and rich history, and what we are still using today is essentially the relational model and relational databases that started to emerge from the 1970s, and they're very prevalent today. In many applications, we also use NoSQL databases, and new SQL databases that are quite recent have started to emerge to combine the disadvantages and advantages of a relational model and the noise scale.